the odds are in your favor. We've all heard this phrase, but in data science, understanding odds can mean the difference between success and failure. Odds ratios are the unsung heroes of logistic regression, providing a powerful tool for interpreting complex relationships in your data. In this video, we'll take you on a journey through the world of odds ratios. You'll learn how to calculate them, interpret them, and most importantly, how to use them to supercharge your data analysis and machine learning models. What if I told you that odds are not what you think they are? Many people use the terms odds and probability interchangeably, but they actually represent different concepts in the world of statistics and data science. Let's unpack this distinction and explore the true essence of odds. Odds are defined as the ratio of the probability of an event happening to the probability of it not happening. This might sound similar to probability, but there's a crucial difference. While probability measures the likelihood of an event occurring out of all possible outcomes, odds compare the likelihood of an event occurring to the likelihood of it not occurring. To illustrate this, let's consider a simple coin toss. The probability of getting heads is 0.5 or 50%, but what are the odds? To calculate odds, we divide the probability of the event happening by the probability of it not happening. In this case, that's 0.5 divided by 0.5, which equals 1. So the odds of getting heads are 1 to 1, or simply 1. This means that heads and tails are equally likely. This distinction becomes even more apparent when we look at events with different probabilities. Imagine a scenario where the probability of success is 0.7, or 70%. The odds in this case would be 0.7 divided by 0.3, the probability of failure, resulting in odds of approximately 2.33. This means that success is 2.33 times more likely than failure. Understanding odds provides a different perspective on event likelihood. While probability gives us a straightforward percentage, odds offer a comparative view. They express the strength of an association between two events, which can be particularly useful in certain types of data analysis. In the realm of data science, odds calculations play a crucial role in various applications. One area where odds are extensively used is in medical research. For instance, researchers might calculate odds ratios to assess the likelihood of disease occurrence in different populations. They could compare the odds of developing a specific type of cancer in individuals with a certain genetic mutation versus those without it. This type of analysis helps identify risk factors and inform medical decisions. Another field where odds are frequently employed is in predictive modeling, particularly in logistic regression. In these models, understanding odds can help interpret the relationships between variables and make predictions about future outcomes. It's important to note that odds can take on a wide range of values, from 0 to infinity. When odds are less than 1, it indicates that the event is less likely to occur than not. For example, odds of 0.5 would mean that the event is half as likely to occur as not occur. On the other hand, odds greater than 1 indicate that the event is more likely to occur than not. The further the odds are from 1 in either direction, the stronger the indication of likelihood or unlikelihood. This range of possible values for odds provides a nuanced way of expressing probabilities. While a probability can only range from 0 to 1, odds can extend infinitely, allowing for more precise comparisons between events with very high or very low probabilities. In data science applications, the ability to work with odds opens up new possibilities for analysis and interpretation. For instance, in a logistic regression model predicting customer churn, odds can help quantify how much more likely a customer is to leave based on various factors. If the odds of churning for customers who haven't made a purchase in the last 6 months are 3, it means they're 3 times more likely to churn compared to those who have made recent purchases. Understanding odds also lays the groundwork for more advanced concepts in statistical analysis. One such concept is the odds ratio, which compares the odds of an event occurring in one group to the odds of it occurring in another group. Odds ratios are particularly useful in case control studies and for interpreting the results of logistic regression models. You've seen how odds can quantify the likelihood of events, but what happens when we pit two sets of odds against each other? This comparison unveils a powerful tool that has revolutionized fields from epidemiology to marketing, the odds ratio. Odds ratios take our understanding of odds to the next level, offering a precise way to measure the relationship between different probabilities. An odds ratio is defined as the ratio of the odds of an event occurring in one group to the odds of it occurring in another group. This simple yet powerful concept allows us to make meaningful comparisons across different populations or scenarios. For instance, imagine we want to compare the odds of a certain health outcome between smokers and non-smokers. The odds ratio would tell us how much more or less likely smokers are to experience that outcome compared to non-smokers. The mathematical formula for calculating odds ratios is straightforward. OR equals open parenthesis odds of event in group A, close parenthesis, divided by open parenthesis odds of event in group B, close parenthesis. This elegant equation encapsulates a wealth of information, enabling us to quantify the strength of associations between variables. Let's walk through a step-by-step example to illustrate how this works in practice. Suppose we're analyzing the effectiveness of a new marketing campaign. We have two groups, customers who were exposed to the campaign, Group A, and those who weren't, Group B. In Group A, 300 out of 1,000 customers made a purchase, while in Group B, 200 out of 1,000 customers made a purchase. Let's calculate the odds ratio. Step 1. Calculate the odds for Group A. Odds A equals open parenthesis 300 divided by 1,000 close parenthesis divided by open parenthesis 700 divided by 1,000 close parenthesis, which is 0.3 divided by 0.7, approximately 0.429. Step 2. Calculate the odds for Group B. Odds B equals open parenthesis 200 divided by 1,000 close parenthesis divided by open parenthesis 800 divided by 1,000 close parenthesis, which is 0.2 divided by 0.8, exactly 0.25. Step 3, calculate the odds ratio OR equals odds A divided by odds B, that is 0.429 divided by 0.25, approximately 1.714. This odds ratio of 1.714 tells us that customers exposed to the marketing campaign were about 1.7 times more likely to make a purchase compared to those who weren't exposed. Understanding the range of possible values for odds ratios is crucial for interpreting results. Odds ratios can extend from 0 to infinity, with each value carrying specific implications. An odds ratio of 1 indicates no difference between the groups. The event is equally likely to occur in both. Values greater than 1 suggest increased odds of the event in the first group compared to the second, while values less than 1 indicate decreased odds. Let's break this down further. If we obtain an odds ratio of 2, it means the event is twice as likely to occur in the first group compared to the second. An odds ratio of 0.5, on the other hand, suggests that the event is half as likely to occur in the first group. This intuitive interpretation makes odds ratios a valuable tool for communicating results to both technical and non-technical audiences. The power of odds ratios lies in their ability to quantify the strength of associations between variables. They provide a standardized measure that allows for comparisons across different studies or populations. This is particularly useful in fields like epidemiology, where researchers often need to synthesize results from multiple studies to draw broader conclusions. Odds ratios have a rich history in statistical analysis, tracing back to their initial applications in epidemiology and clinical research. They quickly became a standard measure for assessing the strength of associations between risk factors and health outcomes. Today, their use has expanded far beyond medicine, finding applications in fields as diverse as marketing, social sciences, and machine learning. One of the key advantages of odds ratios is their versatility in visual representation. Researchers and data scientists can use various methods to illustrate odds ratios, making complex relationships more accessible. Forest plots, for example, display odds ratios along with confidence intervals for multiple studies or groups, allowing for easy comparison. Bar charts and tables can also effectively show the odds in different groups, providing a clear visual representation of the data. In practical applications, odds ratios are often calculated using data from contingency tables. These tables organize observed data into counts of occurrences and non-occurrences for each group, providing a straightforward method for computing odds ratios. This approach is particularly useful when working with categorical data, where events can be classified into distinct groups. The power of odds ratios becomes even more apparent when we consider their role in more advanced statistical techniques such as logistic regression. In these models, odds ratios provide a way to interpret the impact of individual variables on the likelihood of an outcome. This makes them an invaluable tool for data scientists seeking to understand and communicate the relationships within complex data sets. You've seen how odds ratios can compare probabilities, but what happens when we apply them to a model that predicts binary outcomes? This intersection unlocks a new level of understanding in data science, particularly when it comes to logistic regression. Logistic regression is a fundamental technique in the data scientist's toolkit, used when we need to predict an outcome with only two possible results. Think of scenarios like predicting whether a customer will make a purchase or not, if a patient will recover from a disease or not, or if an email is spam or not. These binary outcomes are the bread and butter of logistic regression. But here's where things get tricky. When data scientists run a logistic regression model, they're often faced with a set of coefficients that, at first glance, seem about as clear as a foggy mirror. These coefficients represent the change in the log odds of the outcome for each unit increase in a predictor variable. If you're scratching your head at the phrase log odds, you're not alone. This is where the true power of odds ratios comes into play. Let's break it down. In logistic regression, we're essentially modeling the log odds of an event occurring, but log odds aren't particularly intuitive or easy to explain, especially to stakeholders who might not have a statistical background. This is where the magic of odds ratios happens. By exponentiating these coefficients, we transform them into odds ratios, which are much more interpretable. Here's how it works. Let's say we have a logistic regression coefficient of 0.45 for a particular variable. On its own, this number doesn't tell us much, but when we exponentiate it, that's raising e to the power of 0.45, we get an odds ratio of approximately 1.57. Now we're talking. This tells us that for every 1 unit increase in our predictor variable, the odds of our outcome occurring increase by 57%. Suddenly, we've turned an abstract number into a concrete, actionable insight. Let's look at a real-world example to see how this plays out. Imagine we're analyzing the effectiveness of a new medication. After running our logistic regression, we find that the odds ratio for the medication is 0.64. What does this mean in practical terms? It tells us that for individuals who took the medication, the odds of being diseased are 0.64 times the odds of those who didn't take the medication. In other words, the medication appears to reduce the odds of disease by 36%. This is where odds ratios truly shine in logistic regression. They allow us to quantify effect sizes, giving us a clear picture of how strongly each predictor variable is associated with our outcome. An odds ratio greater than 1 indicates increased odds of the outcome, while an odds ratio less than 1 suggests decreased odds. In our medication example, the odds ratio of 0.64, less than 1, indicates that the medication is associated with lower odds of disease, but the benefits don't stop there. Odds ratios in logistic regression also give us a powerful tool for comparing different predictors. Instead of trying to compare apples to oranges, we now have a standardized measure that allows us to see which variables have the most significant impact on our outcome. This is invaluable when you're trying to determine which factors are most influential in your model. For instance, in a model predicting customer churn, you might find that the odds ratio for time since last purchase is 1.5, while the odds ratio for customer support interactions is 1.2. This immediately tells you that the time since last purchase has a stronger association with churn than customer support interactions. Armed with this information, you can make more informed decisions about where to focus your retention efforts. The process of interpreting logistic regression results can be complex, but odds ratios simplify this by providing a clear metric for understanding the likelihood of outcomes based on predictor variables. They bridge the gap between the abstract world of statistical modeling and the practical world of decision-making. In essence, the relationship between logistic regression, coefficients, and odds ratios is foundational. It transforms the log odds into a more interpretable format that can be effectively communicated to stakeholders, from data team members to C-suite executives. This transformation is what makes logistic regression not just a powerful predictive tool, but also an invaluable aid in strategic decision-making. Now that we've explored the power of odds ratios in logistic regression, it's time to master their interpretation. But beware, this is where many analysts stumble. The ability to accurately interpret odds ratios can make or break your analysis, potentially leading to drastically overstated conclusions if done incorrectly. Let's uncover the common pitfalls that even experienced data scientists can fall into when interpreting odds ratios. One of the most frequent mistakes in odds ratio interpretation is confusing them with measures of risk. This misunderstanding can result in incorrect conclusions about the strength of associations in studies. It's crucial to recognize that odds ratios and relative risk are distinct concepts, each with its own implications and use cases. The distinction becomes particularly important when dealing with common outcomes. In these scenarios, odds ratios can overestimate the risk, leading to misleading conclusions if interpreted as relative risk. For instance, imagine a study examining the relationship between a certain dietary habit and a common health condition. If the odds ratio is 2.5, it doesn't necessarily mean that individuals with this dietary habit are 2.5 times more likely to develop the condition. The actual increase in risk could be substantially lower. To avoid this confusion, it's essential to communicate odds ratios in a way that clearly distinguishes them from relative risk. One effective approach is to use percentages or expected frequencies instead of direct odds ratio values when presenting findings to stakeholders or in reports. This method can enhance understanding and prevent misinterpretation of the data. Another critical aspect of odds ratio interpretation is the consideration of confidence intervals. These intervals provide a range of values that indicate the precision of the estimate. A narrow confidence interval suggests a more precise estimate, while a wide interval may indicate uncertainty about the odds ratio's reliability. Always report confidence intervals alongside odds ratios to give a complete picture of the results. Let's consider an example to illustrate this point. Suppose a study finds an odds ratio of 1.5 for the association between a specific genetic variant and a disease, with a 95% confidence interval of 1.2 to 1.9. This result not only tells us that there's a positive association, but also gives us an idea of how precise this estimate is. The fact that the confidence interval doesn't include 1, which would indicate no association, adds weight to the finding's significance. Interpreting odds ratios for continuous variables requires a different approach. In these cases, the odds ratio indicates how the odds change with each unit increase in the variable. For example, if a logistic regression model examining factors associated with loan approval yields an odds ratio of 1.04 for age, it suggests that for each additional year of age, the odds of loan approval increase by 4%. This interpretation is crucial for understanding the impact of continuous predictors in your model. It's important to note that while odds ratios can be powerful tools for interpretation, they should not be directly interpreted as relative risks, especially when the event in question is common. Doing so can lead to significant misinterpretations of the data. Instead, focus on communicating the direction and strength of the association rather than trying to translate odds ratios into exact risk increases. Another common misinterpretation occurs when researchers fail to distinguish between the odds of an event occurring and the probability of that event. Remember, odds represent the ratio of the probability of an event happening to the probability of it not happening, while probability is simply the likelihood of an event occurring. This distinction is essential for accurate interpretation of statistical results. To illustrate this, consider a scenario where the odds of an event are 2.1. This doesn't mean the probability of the event is 66.67%, 2-3. Instead, it means the event is twice as likely to occur as not occur, which translates to a probability of about 66.67%, 2 plus 1. While the difference may seem subtle, it can lead to significant errors in interpretation, especially when dealing with more extreme odds. When presenting odds ratios, it's often helpful to provide context and comparisons. For instance, if you're analyzing factors associated with customer churn, you might find that the odds ratio for customers who haven't made a purchase in the last 6 months is 3.5, while the odds ratio for customers who have had a negative customer service experience is 2.8. This comparison allows you to communicate that while both factors are associated with increased churn, the lack of recent purchases appears to have a stronger association. While comparing odds ratios can reveal interesting patterns, there's a crucial question we haven't addressed. What if these ratios are simply statistical noise? Let's explore how to separate meaningful insights from random fluctuations in your data. In the world of data science, not all numbers carry equal weight. A large odds ratio might catch your eye, but it doesn't always signify a meaningful relationship between variables. This is where the concept of statistical significance comes into play. Statistical significance helps us determine whether an observed odds ratio is likely to represent a genuine effect in the population, or if it's just a result of random chance in our sample. To assess the statistical significance of odds ratios, researchers often turn to p-values. These values represent the probability of observing an odds ratio as extreme as the one calculated, assuming there's no real effect in the population. A lower p-value suggests stronger evidence against the null hypothesis of no association. Interestingly, there's no universal consensus on the best method for calculating p-values for odds ratios. Researchers may employ various tests depending on their field and specific circumstances. Some common approaches include Fisher's exact test, the chi-square test, and the Wold test. Each has its strengths and limitations, and the choice often depends on factors like sample size and study design. The Wold test, in particular, is frequently used in logistic regression to determine the significance of odds ratios. This test capitalizes on a useful property of odds ratios. The natural logarithm of an odds ratio follows a normal distribution. This mathematical quirk allows us to apply standard statistical techniques to assess significance. However, p-values alone don't tell the whole story. They indicate whether an association is likely to exist, but they don't reveal the precision of our estimate. This is where confidence intervals come into play. A confidence interval provides a range of values that likely contains the true odds ratio in the population. It gives us a sense of how certain we can be about our calculated odds ratio. Calculating confidence intervals for odds ratios involves a bit of mathematical gymnastics, but the concept is straightforward. We begin with the natural logarithm of the odds ratio, add and subtract a multiple of its standard error, and then exponentiate the results. In words, the formula is exponentiation of open parenthesis natural logarithm of OR plus or minus Z multiplied by SE close parenthesis. Here, OR represents the odds ratio. Z is the value from the standard normal distribution corresponding to our desired confidence level, often 1.96 for a 95% confidence interval, and SE is the standard error of the log odds ratio. Let's consider an example to illustrate how we interpret odds ratios along with their confidence intervals. Imagine we're studying the relationship between a new medication and the risk of a particular disease. We calculate an odds ratio of 0.75 with a 95% confidence interval of 0.60 to 0.95. What does this tell us? First, the odds ratio of 0.75 suggests that individuals taking the medication have 25% lower odds of developing the disease compared to those not taking it. The confidence interval provides additional insight. Since the interval doesn't include 1, which would indicate no effect, we can conclude that this association is statistically significant at the 5% level. The lower and upper bounds of the interval, 0.60 and 0.95, give a range of plausible values for the true odds ratio in the population. This interpretation highlights a critical point. If a confidence interval for an odds ratio includes 1, we can't confidently claim that there's a significant association between our variables. In such cases, even if the point estimate of the odds ratio seems large, we must be cautious about drawing strong conclusions. The width of the confidence interval also provides valuable information. A narrow interval indicates a more precise estimate, while a wide interval suggests greater uncertainty. This precision is closely tied to our sample size. Larger samples generally yield narrower confidence intervals, allowing us to make more definitive statements about the odds ratio's true value. Sample size plays a crucial role in determining the statistical significance of odds ratios. With a small sample, even a seemingly large odds ratio might not reach statistical significance due to the inherent variability in the data. Conversely, in very large samples, even small odds ratios can be statistically significant. This underscores the importance of considering both the magnitude of the odds ratio and its statistical significance when interpreting results. So how do we ultimately determine if an odds ratio is statistically significant? We typically look at two key factors: the p-value associated with the odds ratio and its confidence interval. A p-value less than 0.05, or whatever threshold we've set for our study, indicates statistical significance. Similarly, a confidence interval that doesn't include 1 suggests a significant association. When both these conditions are met, we can be more confident that our odds ratio represents a meaningful relationship rather than random noise. While statistical significance helps us interpret odds ratios, their real power lies in their practical applications. From predicting disease outcomes to guiding financial decisions, odds ratios are quietly shaping our world in ways that might surprise you. Let's explore how these numerical comparisons translate into life-changing insights across various fields. In medical research, odds ratios play a crucial role in uncovering the relationships between genetic factors and diseases. Consider a recent study that examined the link between a specific gene mutation and cancer risk. The researchers found that individuals carrying this mutated gene had odds of developing cancer that were 6.88 times higher than those without the mutation. This striking result came from analyzing 356 individuals, where the odds of having cancer for those with the mutated gene were 23 to 117, compared to 6 to 210 for those without it. Such findings can revolutionize our understanding of disease mechanisms and pave the way for targeted treatments and prevention strategies. The impact of odds ratios extends beyond individual health outcomes to shape public health policies on a broader scale. Epidemiologists frequently use odds ratios to identify and quantify risk factors associated with various diseases. This information becomes the foundation for targeted interventions and health campaigns. A prime example is the influence of odds ratio studies on smoking bans in public places. By demonstrating the increased odds of respiratory diseases among smokers, these studies provided compelling evidence for policymakers to implement widespread smoking restrictions, potentially saving countless lives. In the realm of marketing, odds ratios offer valuable insights into consumer behavior, helping businesses optimize their strategies and allocate resources more effectively. Marketing teams use odds ratios to analyze the impact of specific advertisements on purchasing behavior. For instance, a study might reveal that consumers exposed to a particular ad campaign have significantly higher odds of purchasing a product compared to those who weren't exposed. This type of analysis allows companies to fine-tune their marketing efforts, focusing on the most effective channels and messages to drive sales and customer engagement. The financial sector also harnesses the power of odds ratios, particularly in risk assessment models for lending decisions. Banks and other financial institutions use these ratios to evaluate the likelihood of borrower default. By comparing the odds of default between different borrower profiles, lenders can make more informed decisions about loan approvals and interest rates. This statistical approach provides a nuanced understanding of risk factors associated with lending, potentially reducing defaults and ensuring a healthier financial ecosystem. The application of odds ratios has led to groundbreaking discoveries across various fields, often with far-reaching consequences. In healthcare, odds ratios have been instrumental in identifying risk factors for chronic diseases, influencing treatment protocols and preventive measures. For example, understanding the odds ratios associated with lifestyle factors has led to more targeted and effective public health recommendations. These insights have the potential to improve health outcomes on a population level, reducing the burden of chronic diseases and enhancing quality of life for millions. What makes odds ratios particularly powerful is their ability to translate complex data into actionable insights. In fields where understanding risk and behavior is crucial, odds ratios provide a clear, quantifiable measure that can guide decision-making. For researchers and policymakers, this means being able to make data-driven choices that can have profound impacts on public health, consumer behavior, and financial stability. Consider how odds ratios might influence a public health campaign. If a study shows that individuals who engage in regular physical activity have significantly lower odds of developing heart disease, health officials can use this information to design targeted interventions. They might allocate resources to create more public spaces for exercise or implement educational programs emphasizing the importance of physical activity. The odds ratio provides a concrete metric that can justify these initiatives and demonstrate their potential impact. In the business world, odds ratios can drive marketing strategies and product development. A company might use odds ratios to determine which product features are most strongly associated with customer satisfaction. This information could then guide future product iterations, focusing on enhancing the features that have the highest odds of improving customer experience and loyalty. The power of odds ratios also extends to social sciences and policy making. Researchers might use odds ratios to examine the factors associated with educational achievement or employment outcomes. These findings can inform educational policies or job training programs, potentially improving opportunities for individuals and communities. As we've explored the power of odds ratios in various fields, it's crucial to confront a darker aspect of this statistical tool: What happens when these seemingly objective measures are used to make life-altering decisions about individuals? The ethical implications of odds ratio analysis reveal a complex landscape where data science intersects with human lives and societal values. Consider the use of odds ratios in criminal justice systems. While they may promise more data-driven decision-making, their application in areas like bail determination or sentencing can have profound consequences. The crux of the issue lies in the potential for these analyses to perpetuate existing biases. If the historical data used to calculate odds ratios reflects systemic inequalities, the resulting analyses may inadvertently reinforce those very biases. For instance, imagine a scenario where odds ratios are used to assess the likelihood of recidivism among offenders. If the underlying data disproportionately represents certain demographic groups due to historical policing practices, the odds ratios could suggest higher risks for these groups, leading to harsher sentences or reduced chances of parole. This creates a feedback loop where statistical analysis becomes a self-fulfilling prophecy, further entrenching societal disparities. The ethical minefield extends beyond criminal justice. In healthcare, misinterpretation of odds ratios can lead to serious consequences. When odds ratios suggest stronger associations than actually exist, especially for common events, it can result in misguided treatment decisions or unnecessary public alarm. This highlights the critical importance of context in interpreting odds ratios. Experts in the field emphasize that odds ratios should never be viewed in isolation. They must be presented alongside other relevant information, including the prevalence of the outcome being studied and the specific characteristics of the population. Without this context, odds ratios can be misleading, potentially causing public misunderstanding and eroding trust in scientific research. The responsibility of data scientists in this ethical landscape is paramount. It's not enough to simply calculate odds ratios and present them as objective truths. Data scientists must actively consider the potential implications of their analyses, particularly when they inform policies or interventions that affect vulnerable populations. Transparency becomes a key ethical principle in odds ratio analysis. Data scientists have a duty to clearly communicate how odds ratios are calculated, what data was used, and what limitations exist in the analysis. This includes avoiding technical jargon that might confuse non-experts and providing clear explanations of what the odds ratios mean in practical terms. Moreover, data scientists must be vigilant in ensuring that the data used for odds ratio calculations is representative and free from biases that could skew the results. This is particularly crucial in studies that inform public policy or health interventions, where misinterpretation or biased results can have far-reaching consequences. The ethical use of odds ratios also demands a commitment to statistical rigor. Controversies often arise when odds ratios are presented without adequate statistical significance or when they're used to support claims that go beyond what the data actually shows. This can lead to public misunderstanding and mistrust in research findings, especially when odds ratios are oversimplified or sensationalized in media reporting. To navigate these ethical challenges, the data science community has developed guidelines for the responsible use of odds ratios. These guidelines emphasize the importance of thorough data validation, careful interpretation, and clear communication of results. They also stress the need for data scientists to be aware of the potential social impacts of their work and to actively work to mitigate any negative consequences. One key principle is the need for data scientists to consider alternative analyses that might provide a more complete picture. For instance, in cases where odds ratios might overestimate risk for common outcomes, relative risk calculations could provide a more accurate representation of the true effect size. Another important ethical consideration is the need for diversity and inclusivity in data science teams. When the people conducting odds ratio analyses come from diverse backgrounds and experiences, it's more likely that potential biases and ethical issues will be identified and addressed early in the research process. Furthermore, ethical odds ratio analysis requires ongoing education and dialogue within the data science community. As new applications and methodologies emerge, so too do new ethical challenges. Regular discussions and training on ethical data practices help ensure that data scientists remain mindful of their responsibilities and the potential impacts of their work. You've mastered the intricacies of odds ratio analysis, but can you translate that expertise into language a 5-year-old could understand? The art of communicating complex data might be the most valuable skill you'll ever develop. As data scientists, we often find ourselves in situations where we need to explain our findings to stakeholders who may not have a strong statistical background. This is especially true when it comes to odds ratios, which can be particularly challenging to convey effectively. The challenge lies in bridging the gap between statistical precision and real-world comprehension. Odds ratios provide valuable insights, but their true power is unleashed only when decision makers can grasp their significance and apply them to practical situations. So how do we transform these abstract numerical concepts into clear, actionable information? One effective strategy is to translate odds ratios into more relatable terms such as percentages or expected frequencies. Instead of presenting a raw odds ratio, consider expressing it in a way that resonates with your audience's everyday experiences. For instance, you might say, for every year increase in age, the likelihood of loan approval increases by 4%. This approach makes the information more tangible and easier to grasp for non-technical stakeholders. Visual representation can also play a crucial role in communicating odds ratios effectively. Forest plots, for example, are powerful tools that can illustrate both the point estimates of odds ratios and their confidence intervals. These graphical representations can make complex data more accessible, allowing stakeholders to quickly grasp the magnitude and precision of the findings. Bar charts comparing odds across different groups can also be effective in highlighting key differences and trends. When preparing reports or presentations, it's essential to provide context and additional information to support your odds ratio findings. This might include explaining the population studied, the baseline risk, or other relevant factors that can help stakeholders understand the broader implications of the results. By framing the odds ratios within a larger narrative, you can enhance understanding and facilitate more meaningful discussions. However, communicating odds ratios is not without its pitfalls. One common mistake is failing to contextualize odds ratios with other measures, such as relative risk or absolute risk differences. This oversight can lead to misunderstandings about the true implications of the odds ratio, particularly when dealing with common events. To avoid this, consider presenting odds ratios alongside other relevant metrics to provide a more comprehensive picture of the findings. Another potential pitfall is the temptation to oversimplify complex statistical concepts. While it's important to make the information accessible, oversimplification can lead to misinterpretation or loss of important nuances. Strive for a balance between clarity and accuracy, ensuring that your simplified explanations still capture the essence of the statistical findings. When communicating odds ratios, it's crucial to start with the basics and gradually build up to more complex concepts. Begin by explaining the fundamental idea of odds and how they differ from probabilities. Then introduce the concept of comparing odds between groups, which forms the basis of odds ratios. This step-by-step approach can help stakeholders build a solid foundation for understanding the more nuanced aspects of odds ratio analysis. A practical guideline for communicating odds ratios is to start with basic percentages and then explain the odds ratio in relation to these percentages. This method helps bridge the gap between statistical data and real-world implications, enhancing understanding and facilitating more productive discussions with stakeholders. For example, you might begin by stating the percentage of customers who made a purchase in two different groups, then explain how the odds ratio quantifies the difference between these groups. It's also important to address potential misconceptions about odds ratios. Many people mistakenly interpret odds ratios as direct measures of risk, which can lead to incorrect conclusions. Take the time to clarify the distinction between odds ratios and other measures of association, such as relative risk. Explain that while odds ratios are valuable tools for comparing groups, they should not be directly interpreted as probabilities or risk ratios, especially when dealing with common events. When presenting odds ratios, always include measures of uncertainty, such as confidence intervals. These provide crucial information about the precision of your estimates and can help stakeholders understand the reliability of the findings. Explain what the confidence interval means in practical terms and how it affects the interpretation of the odds ratio. Lastly, tailor your communication strategy to your specific audience. Consider their background, level of statistical knowledge, and what they hope to gain from the information. A presentation to a group of marketing executives might focus more on practical implications and actionable insights, while a report for a scientific committee might delve deeper into the statistical methodology. You've learned to explain odds ratios like a pro, but are they always the best tool for the job? Prepare to challenge your assumptions as we compare odds ratios to their statistical cousins and uncover when each measure truly excels. In the world of data analysis, odds ratios are just one of many statistical measures used to quantify relationships between variables. To truly understand their value, we need to examine how they stack up against other common measures like relative risk, risk difference, and hazard ratios. Let's start with relative risk, a measure often used in public health contexts. Relative risk provides a direct measure of the probability of an event occurring in exposed versus unexposed groups. This makes it particularly useful when communicating findings to the general public or policymakers. For instance, saying smokers are twice as likely to develop lung cancer compared to non-smokers is more intuitive than explaining an odds ratio. However, odds ratios have a distinct advantage over relative risk in certain study designs. Case control studies, which are common in epidemiology, can't directly calculate relative risk because they don't measure the incidence of outcomes in the population. Odds ratios, on the other hand, can be calculated from these studies, making them a versatile tool for researchers. But here's where it gets interesting. The relationship between odds ratios and relative risk isn't always straightforward. When events are rare, odds ratios closely approximate relative risk, making them a reliable measure. However, for common events occurring more than 20% of the time, odds ratios can overestimate the relative risk. This discrepancy can lead to misinterpretation of data if not properly understood. Consider a scenario where a new drug is being tested. If the odds ratio suggests that the drug reduces the odds of a common side effect by 50%, it doesn't necessarily mean the actual risk is halved. In such cases, calculating both the odds ratio and relative risk can provide a more comprehensive understanding of the drug's effects. Now, let's turn our attention to risk difference, another measure that complements odds ratios. While odds ratios provide a relative measure, risk difference offers an absolute measure of effect. For example, if a treatment reduces the risk of a disease from 40% to 30%, the risk difference is 10 percentage points. This absolute measure can be particularly useful when assessing the public health impact of an intervention. Hazard ratios, primarily used in survival analysis, offer yet another perspective. Unlike odds ratios, hazard ratios account for the timing of events, making them more appropriate in certain longitudinal studies. For instance, in a clinical trial comparing two cancer treatments, a hazard ratio would not only consider whether patients survived, but also how long they survived. So, When should you choose odds ratios over these alternatives? Odds ratios shine in logistic regression analyses due to their mathematical properties. They allow for adjustments for confounding factors, making them invaluable in complex multivariate analyses. Additionally, their ability to be calculated from various study designs gives them an edge in versatility. However, it's crucial to recognize that no single measure is universally superior. The choice between odds ratios, relative risk, risk difference, or hazard ratios depends on the research question, study design, and the nature of the data. For instance, in a cohort study where the incidence of an outcome can be directly measured, relative risk might be preferred. In a case control study examining rare diseases, odds ratios would be the go-to measure. Moreover, these measures aren't mutually exclusive. In many cases, using multiple measures can provide a more comprehensive understanding of the data. For example, combining odds ratios with risk differences can offer insights into both the relative and absolute effects of an intervention. The key takeaway is that context is king when selecting statistical measures. As data scientists, we must consider not only the mathematical properties of these measures, but also how they align with our research objectives and how they'll be interpreted by our audience. Consider a study examining the relationship between a genetic mutation and cancer risk. While an odds ratio might tell us that individuals with the mutation have 6.88 times higher odds of developing cancer. Combining this with the absolute risk increase and the population prevalence of the mutation would provide a more complete picture for public health planning. In another scenario, imagine you're analyzing customer churn in a subscription-based service. Odds ratios from a logistic regression model might help identify the factors most strongly associated with churn. However, complementing this with a survival analysis using hazard ratios could provide insights into not just whether customers churn, but when they're most likely to do so. Imagine transforming raw data into actionable insights with just a few keystrokes. The tools for calculating odds ratios have come a long way from pen and paper methods, offering data scientists a range of options to suit their needs. But with this power comes a critical question. How do we ensure we're using the right technique for our specific analysis? Let's start with the basics. Manual calculation of odds ratios using a 2x2 contingency table remains a fundamental skill for any data scientist. This method involves organizing data into counts of occurrences and non-occurrences for each group being compared. By calculating the odds for each group and then dividing them, we arrive at the odds ratio. While this approach is straightforward, it becomes time-consuming and error-prone when dealing with large datasets or multiple variables. Enter the world of statistical software, where efficiency meets precision. Popular platforms like R, Python, and SAS have revolutionized the way we handle odds ratio calculations. In R, for instance, the epitools package offers the odds ratio function, which can be applied directly to a contingency table. This not only yields the odds ratio, but also provides confidence intervals, adding a layer of statistical rigor to your analysis. Python users aren't left behind, with the stats models library offering robust tools for odds ratio calculation through logistic regression models. By fitting a logistic regression and exponentiating the coefficients, data scientists can obtain odds ratios for multiple predictive variables simultaneously. This approach is particularly valuable when examining the influence of various factors on an outcome. For those working in clinical research or other fields where SAS is prevalent, the PROCY logistic procedure is a powerhouse tool. It not only estimates logistic regression models, but also outputs odds ratios directly in the results. This feature allows researchers to adjust for confounding variables and obtain confidence intervals, all within a single procedure. While these software solutions offer tremendous power, they also require a certain level of expertise to use effectively. For those seeking a quick estimate or working with simpler data sets, Online calculators for odds ratios can be a tempting option. However, it's crucial to approach these tools with caution. Many online calculators have limitations, such as the inability to adjust for confounding variables or provide confidence intervals. While they may serve for initial exploratory analysis, relying solely on these tools for critical research could lead to oversimplified or potentially misleading results. As we dive deeper into the world of odds ratio calculation, we encounter more advanced techniques that allow for nuanced analysis. Calculating adjusted odds ratios through logistic regression is a prime example. This method enables researchers to control for confounding variables, isolating the effect of a specific factor while accounting for the influence of others. In complex studies where multiple variables may impact the outcome, this approach is invaluable for obtaining accurate and meaningful odds ratios. Continuous variables present their own set of challenges and opportunities in odds ratio calculation. Rather than comparing distinct groups, we're often interested in how the odds change with each unit increase in a continuous predictor. For instance, when examining the impact of age on loan approval, we might find that for each additional year, the odds of approval increase by a certain percentage. This interpretation requires careful consideration and clear communication to ensure stakeholders understand the implications. One powerful technique that bridges the gap between statistical analysis and interpretation is the exponentiation of coefficients obtained from logistic regression. This method provides a straightforward way to interpret the impact of predictor variables on the odds of an outcome occurring. By reporting these exponentiated coefficients alongside their confidence intervals, data scientists can present a comprehensive picture of the relationships within their data. As we navigate this landscape of tools and techniques, it becomes clear that the choice of method for calculating odds ratios isn't just a matter of convenience. It's a critical decision that can significantly impact the validity and interpretability of our results. The best practices for efficient and accurate odds ratio calculation involve a thoughtful approach that considers the nature of the data, the complexity of the analysis, and the intended audience for the results. But even with the right tools and techniques, data scientists can fall into hidden traps that compromise the validity of their odds ratio analysis. Let's uncover the sneaky pitfalls that can turn our insights from illuminating to misleading and learn how to navigate these challenges with confidence. One of the most common mistakes in odds ratio analysis is misinterpreting the odds ratio as a relative risk, especially when the event being studied is not rare. This error can lead to a significant overestimation of the strength of an association between variables. For instance, if a study finds an odds ratio of 2.5 for a particular risk factor, it would be incorrect to conclude that individuals with this factor are 2.5 times more likely to develop the condition. This misinterpretation can have serious consequences, particularly in medical research, where accurate risk assessment is crucial for patient care and public health decisions. To avoid this pitfall, it's essential to communicate odds ratios clearly and distinguish them from relative risks, especially when dealing with common outcomes. One effective strategy is to convert odds ratios into more intuitive measures, such as expected frequencies or percentage changes in risk. This approach can help bridge the gap between statistical findings and practical implications, making the results more accessible to non-technical audiences and reducing the likelihood of misinterpretation. Another major challenge in odds ratio analysis is the impact of confounding variables. These are factors that influence both the predictor and outcome variables, potentially creating spurious associations or masking true relationships. For example, in a study examining the link between coffee consumption and heart disease, age could be a confounding variable if older individuals are more likely to drink coffee and also have a higher risk of heart disease. Failing to account for such confounders can lead to inaccurate odds ratios and flawed conclusions. To address this issue, researchers must be vigilant in identifying potential confounding factors and employ appropriate statistical techniques to control for them. This may involve using multivariable logistic regression models or stratified analysis to adjust for known confounders. Additionally, careful consideration of study design and data collection methods can help minimize the impact of confounding variables from the outset. Multicollinearity presents another significant challenge in logistic regression and odds ratio analysis. This occurs when independent variables in a model are highly correlated with each other, making it difficult to isolate the effect of each variable on the outcome. In such cases, the calculated odds ratios may be unstable or misleading, complicating the interpretation of results. For instance, in a model predicting customer churn, variables such as time since last purchase and customer engagement score might be highly correlated. This multicollinearity could lead to inflated or deflated odds ratios for these predictors, obscuring their true relationship with the likelihood of churn. To mitigate this issue, data scientists should carefully examine the correlations between predictor variables and consider techniques such as principal component analysis or regularization methods to address multicollinearity. Interpreting odds ratios in case control studies poses unique challenges due to the retrospective nature of these studies. Case control designs are particularly prone to selection bias, which can distort the calculated odds ratios. For example, if cases, individuals with the outcome of interest, are more likely to recall or report certain exposures than controls, this recall bias can lead to an overestimation of the odds ratio. To minimize these biases, researchers should strive for rigorous study design, including careful selection of cases and controls, standardized data collection methods, and consideration of potential sources of bias in the analysis and interpretation of results. It's also crucial to acknowledge the limitations of case control studies when reporting odds ratios and to interpret the findings in the context of other available evidence. The rarity or commonness of an outcome can also affect the validity of odds ratio interpretations. When dealing with rare outcomes, odds ratios can provide a reasonable approximation of relative risk. However, for common outcomes, typically those occurring in more than 10% of the population, odds ratios can substantially overestimate the relative risk, leading to exaggerated conclusions about the strength of associations. To address this limitation, researchers should consider alternative measures such as risk ratios or risk differences when analyzing common outcomes. Additionally, it's important to clearly communicate the prevalence of the outcome when reporting odds ratios, allowing readers to gauge the potential for overestimation. Proper study design is fundamental to producing reliable odds ratios. This encompasses not only the statistical analysis, but also the entire research process, from hypothesis formulation to data collection and interpretation. Researchers must ensure that their study design minimizes biases, adequately controls for confounding variables, and uses appropriate statistical methods to produce valid odds ratios. This may involve careful consideration of sample size and power calculations, randomization techniques in experimental studies, and the use of validated instruments for data collection. Furthermore, pre-registration of study protocols and analysis plans can help reduce the risk of selective reporting and post-hoc adjustments that may inflate the significance of odds ratios. You've mastered the basics of odds ratios, but the real world rarely fits neatly into simple models. How do data scientists handle nonlinear relationships or missing data when calculating odds ratios? The answers lie in cutting-edge methods that push the boundaries of traditional analysis. As we venture into advanced topics in odds ratio analysis, it's important to recognize that complex data often requires sophisticated techniques. One such approach involves the use of interaction terms. These allow researchers to explore how the relationship between an independent variable and the outcome variable changes at different levels of another variable. By incorporating interaction terms, data scientists can uncover deeper insights into the intricate relationships within their data. Consider a scenario where you're analyzing the impact of a new medication on blood pressure. While the medication might show a general positive effect, its efficacy could vary significantly based on a patient's age. By including an interaction term between medication use and age in your logistic regression model, you can quantify how the odds ratio for the medication's effect changes across different age groups. This nuanced understanding can lead to more personalized treatment recommendations and improve patient outcomes. Nonlinearity presents another challenge in logistic regression and odds ratio estimation. Real-world relationships often don't follow straight lines, and failing to account for this can lead to inaccurate conclusions. To address this issue, researchers employ several techniques. Polynomial terms can be added to the model to capture curved relationships. For instance, if the effect of age on a health outcome isn't constant, but accelerates or decelerates over time, including age squared as a predictor, can better represent this nonlinear pattern. Spline functions offer an even more flexible approach to modeling nonlinear relationships. These piecewise polynomial functions can adapt to complex shapes in the data, allowing for a more accurate representation of how odds ratios change across the range of a continuous predictor. Additionally, generalized additive models, GAMs, provide a powerful framework for capturing intricate nonlinear relationships without imposing a specific functional form. Missing data is a pervasive issue in real-world datasets, and it can significantly impact odds ratio analysis. Ignoring missing data or using simplistic methods to handle it can lead to biased estimates and unreliable conclusions. Advanced techniques like multiple imputation have become increasingly popular for addressing this challenge. This approach involves creating multiple plausible versions of the complete dataset, analyzing each one separately, and then combining the results to account for the uncertainty introduced by the missing data. Another method for handling missing data is maximum likelihood estimation. This approach uses all available information to estimate model parameters, even when some data points are missing. By incorporating these advanced techniques, researchers can produce more robust estimates of odds ratios in the presence of incomplete data. It's also crucial to conduct sensitivity analyses to assess how different assumptions about the missing data mechanism affect the results, ensuring the stability and reliability of the odds ratio estimates. Bayesian approaches to odds ratio estimation offer a fundamentally different perspective on statistical inference. Unlike traditional frequentist methods, Bayesian analysis allows researchers to incorporate prior knowledge and quantify uncertainty in a more intuitive way. This can be particularly valuable when dealing with small sample sizes or complex models where traditional methods might struggle. In a Bayesian framework, odds ratios are treated as random variables with their own probability distributions. This approach provides a natural way to express uncertainty about the true value of an odds ratio. For example, instead of simply stating that the odds ratio is 2.5 with a 95% confidence interval, a Bayesian analysis might conclude that there's a 90% probability that the true odds ratio lies between 1.8 and 3.2. This nuanced representation of uncertainty can be especially helpful when communicating results to stakeholders or making decisions based on the analysis. The integration of machine learning techniques with odds ratio analysis represents an exciting frontier in data science. Ensemble methods like random forests can be used to identify important predictors in complex datasets, complementing traditional logistic regression approaches. By combining the predictive power of machine learning algorithms with the interpretability of odds ratios, researchers can gain deeper insights into their data. For instance, a gradient boosting model might be used to rank the importance of various factors in predicting customer churn. The top predictors identified by this model could then be incorporated into a logistic regression analysis where odds ratios provide a clear interpretation of each factor's impact. This hybrid approach leverages the strengths of both machine learning and traditional statistical techniques, offering a more comprehensive understanding of the relationships in the data. As datasets grow exponentially larger and more complex, a new frontier emerges in the application of odds ratios. How do we extract meaningful insights from billions of data points without losing interpretability? The answer lies at the intersection of statistical theory and cutting-edge machine learning. The era of big data presents both challenges and opportunities for odds ratio analysis. Traditional methods of calculating and interpreting odds ratios were developed for smaller, more manageable data sets. As we scale up to massive volumes of information, these techniques face limitations in processing power, memory requirements, and computational efficiency. The sheer dimensionality of big data can lead to issues like multicollinearity and sparse data, which can distort odds ratio estimates and compromise their reliability. However, the collision between classical statistical methods and artificial intelligence is not a zero-sum game. Instead, it's creating innovative approaches that leverage the strengths of both worlds. Machine learning algorithms excel at handling large-scale, high-dimensional data and uncovering complex patterns. By integrating odds ratios into these advanced models, we can maintain interpretability while harnessing the power of big data. One area where odds ratios are finding new life is in feature selection for machine learning models. In the vast sea of potential predictors that big data provides, odds ratios can help identify which features are most strongly associated with the outcome of interest. This approach combines the efficiency of machine learning algorithms with the clear interpretability of odds ratios, allowing data scientists to build more focused and explainable models. For example, in a large-scale study of customer behavior, a gradient boosting model might first rank thousands of potential predictors based on their importance in predicting customer churn. The top predictors identified by this process could then be incorporated into a logistic regression analysis where odds ratios provide a clear interpretation of each factor's impact on churn probability. This hybrid approach leverages the strengths of both machine learning and traditional statistical techniques. Ensemble methods like random forests have become popular in big data analysis due to their ability to handle complex interactions and nonlinear relationships. While these models are often considered black boxes, odds ratios can play a role in interpreting their results. By examining the odds ratios of individual predictors across the many decision trees that make up a random forest, data scientists can gain insights into the overall contribution of each feature to the model's predictions. The challenge of explaining black box machine learning models to stakeholders has led to increased interest in model interpretability techniques. Odds ratios are finding a new purpose in this domain. By translating the complex outputs of neural networks or support vector machines into odds ratios, data scientists can provide more intuitive explanations of how changes in input variables affect the predicted outcomes. This approach bridges the gap between sophisticated machine learning algorithms and the need for clear, actionable insights in business and policy decisions. Calculating odds ratios in high-dimensional data environments poses unique challenges. The potential for overfitting increases dramatically as the number of variables grows, potentially leading to unreliable or misleading odds ratio estimates. To address this, researchers are developing advanced regularization techniques specifically designed for odds ratio estimation in big data contexts. These methods help to stabilize estimates and improve the reliability of odds ratios even when working with thousands or millions of predictors. Emerging techniques are pushing the boundaries of how odds ratios can be used in big data environments. One promising approach involves the integration of odds ratios directly into machine learning algorithms. For instance, some researchers are exploring ways to incorporate odds ratio calculations into the loss functions of neural networks, creating models that optimize for both predictive accuracy and interpretability. This fusion of traditional statistical measures with cutting-edge AI techniques represents a new frontier in data analysis. Another innovative application is the use of odds ratios in explaining the decisions of complex AI systems. As machine learning models are increasingly used in high-stakes decisions like medical diagnoses or credit approvals, there's a growing need to understand and justify their outputs. By calculating odds ratios for the key features influencing a model's decision, data scientists can provide stakeholders with a familiar and interpretable measure of impact, even when the underlying algorithm is highly complex. The synergy between odds ratios and machine learning is also evident in the field of causal inference. While machine learning excels at finding patterns and making predictions, it often struggles with questions of causality. Odds ratios, with their roots in epidemiology and their ability to quantify associations while controlling for confounding factors, can complement machine learning approaches in teasing out causal relationships from observational data. This combination is particularly powerful in fields like healthcare and social sciences, where understanding the drivers of outcomes is crucial. As we navigate this new landscape, it's clear that odds ratios are not becoming obsolete in the age of big data and AI. Instead, they're evolving and finding new relevance. By combining the interpretability of odds ratios with the power of machine learning, data scientists are developing more robust, explainable, and actionable insights from complex data sets. This hybrid approach allows us to harness the full potential of big data while maintaining the clarity and interpretability that odds ratios provide. As we stand on the cusp of a new era in data science, the future of odds ratio analysis promises to be both exciting and transformative. While odds ratios have long been a staple in fields like epidemiology and marketing, their potential is far from fully realized. The next frontier of data science may see odds ratios evolving into dynamic predictive tools that reshape our understanding of risk and probability. One of the most intriguing developments on the horizon is the emergence of techniques for dynamic odds ratio estimation in real-time data analysis. These methods could revolutionize how we interpret and respond to rapidly changing situations in fields such as healthcare and finance. Imagine a world where odds ratios update continuously as new data streams in, providing decision makers with an ever-evolving picture of risk and opportunity. This could lead to more responsive and timely insights, enabling professionals to make split-second decisions based on the most current information available. The integration of causal inference methods with odds ratio analysis is another area ripe for exploration. As datasets become increasingly complex, understanding the true relationships between variables becomes more challenging. Causal inference techniques could enhance the interpretation of odds ratios by providing a clearer picture of how different factors interact and influence outcomes. This could be particularly valuable in fields like social sciences and public policy, where untangling the web of causal relationships is crucial for effective decision-making. In the realm of healthcare, odds ratios are poised to play a pivotal role in the advancement of personalized medicine. By leveraging individual patient profiles and vast amounts of medical data, odds ratios could be used to tailor treatments with unprecedented precision. This could lead to more effective healthcare interventions, as doctors would be able to assess the likelihood of success for different treatment options based on a patient's unique characteristics and medical history. The future may also bring significant advancements in how we visualize and communicate odds ratios. As data becomes more complex, the need for clear and intuitive ways to present statistical concepts to non-experts becomes increasingly important. We might see the development of interactive graphics and user-friendly software tools that make odds ratios more accessible to a wider audience. These tools could help bridge the gap between data scientists and decision makers, ensuring that insights derived from odds ratio analysis are accurately understood and applied. The integration of odds ratios with other advanced statistical measures and machine learning algorithms is another exciting prospect. By combining the interpretability of odds ratios with the power of techniques like Bayesian methods and neural networks, data scientists could develop more robust and comprehensive analytical frameworks. This fusion of approaches could enhance the applicability of odds ratios in complex data environments, allowing for more nuanced and accurate predictions. As data science continues to evolve, odds ratios are likely to maintain their crucial role in interpreting complex relationships within big data. However, their application may expand beyond traditional fields like epidemiology and social sciences. We might see odds ratios being used in novel ways to analyze high-dimensional and unstructured data, opening up new avenues for insight in areas like natural language processing or computer vision. The development of new statistical frameworks that better accommodate the nuances of modern datasets is another potential direction for the future of odds ratio analysis. These frameworks could address challenges posed by high-dimensional data, nonlinear relationships, and the increasing prevalence of unstructured information. By adapting odds ratios to these new data landscapes, researchers could unlock insights that were previously hidden or difficult to quantify. As we approach the culmination of our exploration into odds ratios, it's time to put your understanding to the test. The journey through this powerful statistical tool has been complex, but the real challenge lies in mastering its application in real-world scenarios. Let's synthesize what we've learned and uncover the core principles that separate novices from experts in the world of odds ratios. At its essence, the odds ratio is a comparative measure calculated by dividing the odds of an event occurring in one group by the odds of it occurring in another. This simple calculation belies the profound insights it can provide across various fields of study. An odds ratio greater than 1 indicates that the event is more likely to occur in the first group compared to the second, while a value less than 1 suggests the opposite. However, interpreting these numbers requires a nuanced understanding that goes beyond mere calculation. One of the key takeaways in mastering odds ratios is recognizing the distinction between association and causation. Researchers often emphasize that odds ratios do not imply causation, but rather highlight an association between variables. This distinction is crucial when applying odds ratios in fields such as epidemiology, marketing, or social sciences, where misinterpretation can lead to flawed conclusions or misguided policies. Context plays a pivotal role in the accurate interpretation of odds ratios. The same numerical value can have vastly different implications depending on the population and conditions under study. For instance, an odds ratio of 1.5 for a rare disease might represent a significant finding, while the same value for a common condition could be less impactful. This contextual understanding is what sets apart skilled analysts from those who merely perform calculations. The versatility of odds ratios across different fields is a testament to their power as an analytical tool. In epidemiology, they help identify risk factors for diseases. In marketing, they can quantify the effectiveness of advertising campaigns. In social sciences, they might reveal patterns in educational outcomes or employment trends. This broad applicability underscores the importance of mastering odds ratios for data scientists working across diverse domains. However, with great power comes great responsibility. Ethical considerations are paramount when working with odds ratios, particularly in sensitive areas such as public health and criminal justice. Misinterpretation or misuse of odds ratios can lead to harmful consequences affecting individuals and communities. Data scientists must be acutely aware of the potential impact of their analyses and strive for transparency in their methods and interpretations. Mastering odds ratios involves more than just understanding their mathematical properties. It requires a holistic approach that considers the context of their application, the limitations of the data being analyzed, and the ethical implications of their use in research and decision-making. Comprehensive guidelines for effective odds ratio use include ensuring clarity in communication, avoiding common pitfalls in interpretation, and being aware of the constraints and potential biases in the underlying data. As we move into an era dominated by big data and artificial intelligence, the relevance of odds ratios remains undiminished. In fact, their role may become even more critical as we grapple with increasingly complex datasets and sophisticated analytical techniques. Odds ratios can serve as a bridge between advanced machine learning models and interpretable insights, helping to explain the decisions of complex AI systems in terms that stakeholders can understand. The core principles for effective use of odds ratios in data science are multifaceted. First, maintain a critical perspective on the data and its limitations. Second, always consider alternative explanations and potential confounding factors. Third, communicate results with clarity and context, avoiding oversimplification. Fourth, be transparent about methodologies and assumptions. Finally, remain vigilant about the ethical implications of your analyses, particularly when they may impact vulnerable populations. Now that we've explored the theoretical foundations of odds ratios, it's time to put your knowledge into practice. While understanding the concepts is crucial, true mastery comes from hands-on experience with real-world data and scenarios. Let's challenge your analytical skills and push the boundaries of your odds ratio expertise. Our first exercise draws from a health survey dataset where we'll examine the relationship between smoking habits and the development of lung cancer. Imagine you have data from 1,000 participants with 500 smokers and 500 non-smokers. Among the smokers, 50 have developed lung cancer, while among non-smokers, 10 have developed the disease. Your task is to calculate the odds ratio and interpret its meaning in this context. Remember to consider the confidence intervals and statistical significance of your results. As we progress, we'll tackle more complex scenarios. Consider a genetic study investigating the link between a specific gene mutation and cancer risk. In this dataset, 34 out of 356 individuals with the mutated gene have developed cancer. Your challenge is to calculate the odds of cancer for those with and without the gene mutation, then determine the odds ratio that quantifies the risk associated with this genetic factor. But calculating odds ratios is just the beginning. A critical skill for data scientists is the ability to identify and avoid common pitfalls in interpretation. Let's explore a scenario where the odds ratio might be mistaken for relative risk. Suppose you're analyzing data on a common health condition that affects 30% of the population. If your odds ratio calculation suggests a 2.5 times higher odds for a particular risk factor, how would you explain this result to avoid overestimating the actual risk increase? Communication is key in data science, and translating statistical findings into actionable insights is a valuable skill. Your next challenge is to take the results from our gene mutation study and craft a clear, concise explanation for 3 different audiences: fellow data scientists, medical professionals, and patients with no statistical background. How would you adjust your language and presentation to effectively convey the implications of your analysis to each group? To further hone your skills, let's dive into a case study from the field of epidemiology. You're tasked with analyzing the effectiveness of a new medication in reducing the risk of a specific disease. The study involves 1,000 participants split evenly between those taking the medication and a control group. Your analysis reveals an odds ratio of 0.64 for the medication group. How would you interpret this result? And what additional information might you need to provide a comprehensive assessment of the medication's efficacy? As we advance, it's crucial to recognize the limitations of odds ratios and know when to employ alternative measures. Consider a scenario where you're studying a common outcome, such as the prevalence of a particular side effect in a widely used medication. How might the use of odds ratios potentially mislead in this context? And what alternative approaches could you suggest to more accurately represent the risk? Let's also explore the application of odds ratios in non-medical fields. Imagine you're working with a tech company to analyze user engagement with a new feature. You have data on various user characteristics and their likelihood of using the feature regularly. How would you apply odds ratio analysis to identify the factors most strongly associated with feature adoption? What challenges might you encounter in interpreting these results, and how would you address them? For our final exercise, we'll tackle a complex data set with multiple variables and potential confounding factors. You're given a large data set on customer churn for a subscription-based service, including demographic information, usage patterns, and customer support interactions. Your task is to conduct a comprehensive odds ratio analysis to identify the key factors associated with churn risk. How would you approach this analysis, accounting for potential interactions between variables and ensuring the validity of your results? Throughout these exercises, it's essential to maintain a critical perspective on the data and its limitations. Always consider alternative explanations and potential confounding factors. Strive to communicate your results with clarity and context, avoiding oversimplification. Be transparent about your methodologies and assumptions, and remain vigilant about the ethical implications of your analyses, particularly when they may impact vulnerable populations. You might think you've mastered odds ratios by now, but the truth is the most powerful insights are still waiting to be uncovered. The world of statistical analysis is vast and ever evolving, and staying at the cutting edge requires a commitment to continuous learning. Fortunately, there's a wealth of resources available to help you transform your understanding of odds ratios from proficient to exceptional. Let's start with video content, which can be an excellent way to reinforce and expand your knowledge. The YouTube video Mastering Odds Ratios in Logistic Regression, a step-by-step guide, offers a comprehensive breakdown of odds and odds ratios, presenting these concepts in a clear and structured manner. For those looking to deepen their understanding of statistical relationships, odds ratios and log odds ratios, clearly explained, provides a detailed explanation of how odds ratios are calculated and interpreted. If you're particularly interested in effectively communicating odds ratios, especially in medical and health research contexts, a guide to odds ratios, what they are and how to communicate them clearly, offers practical examples and strategies. For a more structured learning experience, online courses can provide both theoretical knowledge and practical applications. Platforms like Coursera and edX offer modules on logistic regression and odds ratios as part of broader data science and statistics courses. For instance, the data science specialization on Coursera and Introduction to Statistics on edX both cover these topics in depth. These courses often include hands-on exercises and projects allowing you to apply your knowledge to real-world scenarios. To stay current with the latest developments in statistical methods, including odds ratio analysis, consider engaging with professional organizations. The American Statistical Association, ASA, and the Royal Statistical Society, RSS, regularly host conferences and workshops that cover advanced statistical techniques. These events not only provide access to cutting-edge research, but also offer valuable networking opportunities with experts in the field. When it comes to practical application, having the right tools at your disposal is crucial. Statistical software packages like R and Python offer libraries specifically designed for calculating and interpreting odds ratios. In R, the EpiTools package provides functions for odds ratio calculations, while the GLM function can be used for logistic regression analysis. Python users can turn to the Stats Models library, which offers similar capabilities for logistic regression and odds ratio calculations. For those moments when you need quick answers or want to discuss complex problems, online communities can be invaluable resources. Platforms like Stack Overflow and Cross-Validated, part of Stack Exchange, are excellent forums for discussing advanced statistical methods, including odds ratios. Here you can ask questions, share insights, and learn from experienced statisticians and data scientists. Additionally, Reddit's R Statistics community provides a platform for valuable discussions on various statistical topics. As you continue to expand your knowledge, it's important to remember that mastering odds ratios is an ongoing process. The field of statistical analysis is constantly evolving, with new methodologies and applications emerging regularly. Staying updated with the latest developments is crucial for any practitioner looking to maintain their expertise. One way to keep your skills sharp is by regularly engaging with academic literature. Scholarly journals in statistics, epidemiology, and data science often publish articles that push the boundaries of odds ratio analysis and its applications. While these papers can be challenging, they offer insights into cutting-edge techniques and novel approaches that you might not encounter in more general resources. Another valuable approach is to seek out case studies and real-world applications of odds ratio analysis across different fields. This can help you understand how these statistical tools are applied in various contexts, from medical research to marketing strategies. By examining how odds ratios are used to solve diverse problems, you can develop a more nuanced understanding of their strengths and limitations. Don't underestimate the power of practical experience. As you learn new concepts and techniques, try to apply them to your own projects or datasets. This hands-on approach can help solidify your understanding and reveal nuances that might not be apparent from theoretical study alone. Consider participating in data science competitions or contributing to open source projects that involve odds ratio analysis to further hone your skills. Lastly, remember that learning is often most effective when it's collaborative. Consider forming or joining a study group with colleagues or peers who share your interest in statistical analysis. Regular discussions and problem-solving sessions can help reinforce your knowledge and expose you to different perspectives and approaches. As we conclude our exploration of odds ratios, it's clear that this statistical concept is more than just a theoretical abstraction. It's a powerful tool that can significantly enhance your ability to interpret complex data relationships and make informed decisions based on statistical evidence. By mastering odds ratios, you're equipping yourself with a versatile skill that's essential for effective communication of research findings, particularly in fields like medical research, where they can indicate strong associations and lead to impactful health interventions. The true power of odds ratios lies in their ability to transform raw data into actionable insights. Whether you're analyzing customer behavior, evaluating medical treatments, or assessing risk factors, odds ratios provide a clear, quantifiable measure that can guide decision-making across various fields. As you move forward in your data science journey, challenge yourself to apply this newfound knowledge in your next project. By doing so, you'll not only deepen your understanding, but also unlock new possibilities for data-driven discoveries and innovations.